maybe I want just to say very fast. So phases we did show the phases, yes? That it's a simple curve for kappa smaller than 4, and then it surrounds points for kappa between 4 and 8. Did we show that? I lost my bookmark. Yeah, Besser process. So did I show that between 4 and 8 it swallows points, or did I not? What was the last thing? Yes, yeah, okay, yeah. So it's okay. Let me maybe. Did I do the calculation, the crossing calculation? What is the? Yeah, I think I did. Yeah, I think I did. Yeah. So now I think I recall. Okay. So just maybe one more calculation, but so did I have I finished the calculation that it swallows together 2 points, let's say x and y? Yes. Yeah. Okay. Yeah. So that also does the crossing estimates in other models. So maybe then the one thing which I want just to briefly discuss, I don't want to give the proof, but I should want to give the idea of the proof. So I gave examples of calculating probability of some event. Now there are more complicated things like Hausdorff dimension of the SLE curve. So I don't want to do the proof. The proof would probably take like 2 hours. There is, well, maybe 3 hours because there is some technical part. But I want just to show that actually it's more or less the same. You also reduce to an equation. So how to calculate dimension? With the dimension of gamma. So the theorem is by Van Salm-Befara that Hausdorff dimension of the curve SLE curve is 1 plus kappa over 8 when kappa is smaller than 8, and 2 when kappa is at least 8. So the proof, or rather the idea of the proof, so more or less, what does it mean that Hausdorff dimension of gamma is something, let's say d? It more or less means for a random gamma. Well, it's the Hausdorff dimension of gamma equal to d means if I take gamma and I superimposed a grid with size epsilon, so we just superimpose epsilon grid. So it more or less means that gamma is covered by approximately 1 over, well, if the grid size is epsilon in a box 1 by 1, you will have 1 over epsilon by 1 over epsilon squares. So dimension d means that gamma is covered by power d of those. So we have 1 over epsilon by 1 over epsilon. If power 2, then all the squares are needed, then you have dimension 2. If you have a point dimension 0, you need 1 square. If you have a smooth curve, it's 1 over epsilon to the power 1. Well, approximately you need to put limits and all that out of 1 epsilon squared squares. And that is more or less equivalent to the fact that if that portion of squares covers gamma, if I take a random square, so the probability that a random square intersects gamma is approximately, well, I should divide one by another, 1 over epsilon to the power d over 1 over epsilon to the power 2. So it will be epsilon to the power 2 minus d. So if gamma has dimension 2, then with probability close to 1, random square will intersect it. If gamma has dimension 1, with probability close to epsilon. So this is more or less true for any curve gamma, but my curve gamma is random. So instead of saying random square intersects gamma, more or less I can say just a fixed square intersects random gamma. So, that is true for any gamma, and this is true for any gamma. And then for a random gamma, which we have probability that a given square intersects a random gamma is approximately epsilon to the power 2 minus d. It's here there is so it's all a bit hand waving. There is one sort of rigorous thing one has to do to make it rigorous. You need here you need some correlation estimate. What do I mean? So what can happen? What usually happens if we have this thing? Well, usually happens that with 100% probability we intersect that number of squares and everything is fine. But you can also arrive at this number in a different fashion. That with 1% probability you intersect 100 times this, and with 99% you intersect nothing. So you have a set which is 99% of the cases is empty, and in 1% of cases is 100 times as fat. Even better, it's has one more dimension, but with probability epsilon, and with the rest probability 1 minus epsilon, it has dimension 0. So it's to exclude something like with probability equal to epsilon, we intersect more. So how do I? So that this thing sort of happens simultaneously for all squares. So it's either all squares intersect or all squares don't intersect. So so includes something like with probability equal to epsilon 2 minus d, gamma is equal to the full complex plane, and with probability 1 minus epsilon 2 minus d, gamma is empty set, to exclude something like that. That on average then it has dimension d, but in fact it's just with very small probability it has dimension 2, and otherwise it is nothing. So we need to exclude something like that, and for this you need some sort of correlation estimate, that probability that gamma intersects, well, let's say one square q and another square p intersects q and p, is some bound from above. So usually it's a sort of a bound, like distance from p and q to the power something. So and there are whole books written about how you do that, both in fractal geometry and in probability theory. So if you want really to study variables and you know expectation for variable for this cube, for this cube, for this cube, how much do we need to decorrelate them to make some conclusions? So that's very surprisingly, that was the difficult point. So everyone knew how to calculate and get the correct value of d, but what took Vincent Befar 2/3 of his thesis is to do this decorrelation, to do the correlation estimate to show that probability that a CLE visits two cubes is when they are far away, they basically it's unrelated probability that they visit them. So that I honestly I don't even know a short solution nowadays, because you can, for these probabilities, you can also write equation, but it will be equation which depends on 2 points in the plane. So there are 4 real coordinates, so it's more complicated to solve. We don't know exact solution, we weren't able to guess. So we need to write estimates, and the way we write estimates, they are not, how to put it mildly, satisfactory. So it's rather lengthy, but it's not difficult, but it requires lots of writing. So what I want to explain before we do some model is how do you get this probability that you pass through, so how to get the last probability then. So what do you do that probability that a given square intersects SLE? So basically it's what we need is to get that the, let's say, probability that the distance of, let's say, probability that the distance from Z to the gamma curve is smaller than epsilon. And this probability is approximately epsilon to the power 2 minus D. And then D will be the dimension. And this is if you do the expectation of this distance to some power, let's say distance, let's say expectation of, let's say 1 over distance Z gamma to the power alpha. So this expectation will be finite or infinite. If you have this thing, you just look which thing could be integrated, and essentially it means that when alpha is bigger than 2 minus D, you will have finite expectation. When alpha is smaller than 2 minus D, you will have infinite expectations, because 1 over x is not integrable on a line. So what I write now, it's sort of, if you have correlation estimate, then it's just with some work, it's rigorous equivalences. If you don't have correlation estimates, that's what physicists would do in a statement like that. They would just sort of rewrite the way it's easier to compute. So the question is, well, okay, so here is our curve. It can touch itself, and there is point Z, and we want to study distance from Z to our curve. And what we can, well, the question is, if I want to do the same martingale trick, so I open up this part of the curve, and the rest of the curve will look something like that. So it looks something like this. So this is GT, this is GT of Z. So what happens to the distance when I apply GT of Z? We have Kirby distortion theorem. So the distance is basically multiplied by G prime. So this quantity itself is not a martingale. We cannot do the same thing as before, because the distance is rescaled. But it's a martingale up to multiplication by G prime. And of course, the Kirby theorem, so it doesn't exactly say that it's exactly equal. So it's actually better to do what is called by Kirby the conformal distance. So let's map this by the map phi to a unit disk, just this component, and Z to the center, phi of Z. Then Kirby tells us that the ratio of the distances, here it's 1 and here is the distance D, is equal to phi prime. So Kirby tells us that up to a factor 4, 1 over distance from Z to the power gamma is comparable to phi prime. So even up to a factor 4. So what we can do, we can just do here expectation of phi prime of Z to the power alpha. It will be exactly the same up to factor 4 to the power alpha. And we need to understand whether it's finite or infinite. What you can sort of see that the value of phi prime from this point and from that point, it differs exactly by the value of gt from this point to that point, because gt times this phi is that phi. So this is, well, will be the same in that case. It is the same as expectation. We run gam 0t up to time t, and then you have expectation of conditional distance. But that we can conformal invariance map there, and we get expectation of gt prime of z times phi of gt of z to the power alpha. So this is the thing which is a martingale. So the yeah, okay, so that's, so this is the thing which is a martingale. So we can write that the drift of this guy, g prime t of z to the power alpha phi of z, so has zero drift. And that will give us a PDE very much like before. So the only difference, the only complication is that before we studied something conformally invariant, which when you map it's conformally invariant. And this time we study something conformally covariant. When we map, we multiply by derivative to the power alpha. So when you do eta differentiation, well, d phi you do exactly like before, but there is also d of this term which you need to write down. And d of this term is very easy to write down, because what was the dg t of z is 2 over gt of z dt minus square root of kappa dbt. And you can take the space derivative. And the space derivative commutes with this eta derivative. So this thing, space derivative, will be twice gt prime of z over gt of z squared minus sine dt. And this will just disappear because it doesn't depend on point z. So this thing is easy to differentiate. Well, there is also absolute value. You have to work out how to differentiate under absolute value, but that is doable. So basically, the only difference is that we used to have a PDE, so it will be again a function of the argument of z. So it's if z is r to the power I theta, you can write then again by conformal invariance phi of r to the power ei theta is equal to, well, let's say another letter phi of theta, and then when you rescale by factor r, you get what? You get r to the power alpha, yeah. G prime t or to the power minus alpha. So the bigger, yes, yeah, like that. And then what you get an equation which will be again second derivative of theta plus something first derivative of theta, but this time there will be just, well, phi. There will be just phi, a new term, phi itself. And the phi itself will be because you also have this term. So the equation will be slightly more difficult to solve, because before we could just rewrite it as a logarithmic derivative, and now it will be a general second order ODE. I have it here, but I don't want to write. And the slightly easier thing is that you, well, you basically know what should happen. It should have solutions when alpha is more than 1 minus kappa over 8, and no solutions when it's bigger, so you get this. So this is something which I don't want to do in all details. Once again, there is a part where you get the answer, where you solve the equation, and the only difference with before is that it's covariant. And then there is a correlation part where you have to show in some way, say by solving equation or by doing some geometry, that probability that a silly visits two cubes far away is basically uncorrelated. So the further they are away, the less correlation is between these visits. Okay. Now what I really want to show today and in a week is convergence to some lattice models. So I will start with two of those. And the one model, the first model, is very much related to delay and other Laplacian growth. So it can be, so let's say the first model, it's called sometimes Laplacian random walk. A random walk. So we do it on a grid. So we have a discrete domain. It can be in principle the whole plane. So we have some point B, which is the target. And then we have the point, let's say we draw on some curve, the point A where we start. So we want to draw a walk which goes from A to B, well, let's say at time t we reach this point. So what we can do here? We can go in three different directions. So we do discrete domain omega, well, can be the full plane. So, for example, it would be square lattice. So we want to draw a curve, a simple curve, from A to B. Once we have already the curve A, A1 and so on, AT, choose AT plus 1 out of neighbors of AT. So we need to choose one of these 3 points. And the question is, proportionally to what do we choose? So the idea is that we choose proportionally to the harmonic measure of these 3 points as viewed from the point B. So we choose, well, let's say they are neighbors. Let's say what are the good letters? U1, U2, U3. So probability of UK is a harmonic measure of UK viewed from B over sum of these harmonic measures. Or better yet, I write as a Green's function because we're in the discrete setting and later it will work better. So its probability is proportional to the Green's function of this domain omega minus this curve which I have written of points UK and B.
B is on the boundary.
Yes, yeah. So this is sort of a strange model. I would say that the diffusion limited aggregation which we mentioned, it was a similar model, but what you did, you you draw not a curve, but you draw some aggregate, and then you could attach points anywhere to this aggregate. And this is indeed very physical. You see it quite often. Well, you can see it when crystals grow, that just molecules are attached in a random place and grows. Here we condition on it growing as a curve. So that's in a sense a bit strange, and I know physical situations where something like this happens, but they are much less rare. And it turns out that exactly the same year another model was defined. And it's very difficult to go from this model to another model, but it's very easy to go from the second model to the first one. So the second model is called loop-erased random walk. Yeah, by the way, in principle, you can put here some power. So there are people, so also we can do alpha Laplacian random walk, where probability of UK is proportional to this g to the power alpha. But so far we know basically nothing about it. So we know only something about alpha equal 1. And loop-erased random walk is a different model. So what we do random walk from A until we hit B. So it looks something like that. So I do the random walk. So this is an example. It gives me a random curve. Yeah, by the way, both models in principle you can do with different boundary conditions. You can say that, let's say, take this part of the boundary and look at harmonic functions which satisfy Dirichlet condition there, or Neumann condition, or oblique Neumann condition, or something. So there are variations. So you can have, and that will have some physical meaning. So here I just do like the usual random walk. So I take this domain. I just think about it as a graph, not embedded in the plane, and I do random walk on this graph from this point until I hit this. If domain is embedded into the plane, in reality, well, we'll see it later, it actually means essentially Neumann boundary conditions, that if you hit the boundary, you get reflected back into the domain. It's the same as if there is no boundary there. Okay, so the question which was asked by Loewner, and Loewner observed that these two models are the same. So he wanted to study self-avoiding walk. And self-avoiding walk is a model where you just do all, you just take all the simple curves from A to B. Yeah, maybe just a small remark. Introduced by Loewner to model self-avoiding walk. Now, what is self-avoiding walk? Self-avoiding walk, basically, you take all simple curves from A to B. And that's a famous model which was introduced by Paul Flory in chemistry as a model for position of polymer molecules. So sometimes you call self-avoiding polymer this model. And there is a tricky thing that either you can do them all equally likely, all the simple curves, or in reality it's better, so there are two possibilities. Either you do equally likely all the curves, so you should count how many of them are there. And then it turns out that there will be specific lengths which will be favored by this model, which depends on the size domain. Or you can wait, the interesting way is that the weight will be 1 over mu to the power length, and you should calculate the mu which is appropriate for this lattice, but then it also appears that there is a weight which depends on the points here and here, so there is also some weight which is length to some funny power. Well, there are different powers. For example, if it's no boundary, it's 11/32 if you start from there. So then, in principle, you should also introduce some weight. But this model is much more difficult. It's much more difficult because it's not a Markov process. You cannot draw self-avoiding curve from left to right, because if you start drawing self-avoiding curve, suppose I draw simple curve from left to right and arrive at this situation. Well, in this situation, I can make one more step, and then I'm done. There is no self-avoiding way out. But if I draw it like this, here there are three possible ways, and I can continue in many ways. So the problem with self-avoiding curve is that if you really want to study them, you need to keep the whole history. So Loewner wanted to get rid of this requirement, wanted some simpler model. And what he suggests is that well, you can do this, and he didn't know how to address then the problems. But he thought that we know everything about random walk, so let's do random walk, and then erase loops. Now, how do we erase loops? Well, there are many loops here, and I see that it goes over and over, so there should be some canonical way to do it. So do it chronologically. We go left to right. If we draw a loop, we immediately erase it. So erase loops chronologically. So what happens in reality? So we go. I arrive here, it's a loop. So I have to erase it. So this part remains so far. Now I go. Here it's not a loop because I already erased this part, so it's not important. I haven't formed the loop yet. But when I arrive here, I form the loop. So I erase it. I go. It's not a loop. I arrive here, I erase this. I go. Well, this I have to erase. I go. This I have to erase. And then I arrive. So the final curve will be, well, you see what it will be a simple curve. So it's very easy. You draw a curve, but each time when you complete a loop, you erase it. And you start from not the clean slate, but what you have drawn up to that time. So the remark is that it's not an easy procedure. So for example, loop erasure from A to B in general is not the same as loop erasure from B to A. They are different. So you get different results. And a priori it looks like this is something which on one hand is easy because it's related to random walk. On the other hand, it's difficult because to proceed to the next step, you run for a very long time, you create something, and then you maybe erase it. So if I've drawn, it can in principle happen that I draw my curve up to this point, and then I start moving, and it goes like this, and hits here, and I have to erase everything I've done up to now, and restart. But then it has this sort of strong Markov property in the sense that, I'm back to this place where I've already been, but it's basically the same Markov chain. I just try another time. So it's basically, you have a Markov chain, but certain steps force you back, like in this snakes and ladders children's game. But you're again back to the same point, and you just should calculate what are the trajectories which escape from it to be. So it doesn't matter that you erase. So suppose that with probability 1/3 you erase this thing, but then you are back again, you do this 2/3 when you don't erase, and so on and so on and so on, and eventually you will hit B. So that's the second definition. And the theorem of Loewner is that they coincide. So theorem Loewner. So Laplacian random walk is equal to loop erased random walk. And it's fairly easy if you start with loop erased random walk, because you can just try to calculate probabilities to go in 3 directions. And as we'll see in a minute, you immediately get these Green's functions probabilities. It's incredibly difficult if you start from Laplacian random walk. If I draw Laplacian random walk and ask, is there some simple way to arrive at it? I'm not sure that person who doesn't know about loop erased will guess it. So proof. So I want to once more emphasize what is the definition of loop erased random walk. So what is the random walk in omega from A to B? You take all walks gamma from A to B, now the weight of a walk gamma is, so for example, on a square lattice, the weight of gamma will be 1 over 4 to the power length gamma. On triangular lattice, 1 over 6 to the power length gamma. On hexagonal lattice, 1 over 3 to the power length gamma. If I have arbitrary graph, each step I should put 1 over 4 or 1 over 3 or 1 over 5, depending on the number of neighbors. Or, well, strictly speaking, product over all vertices V in gamma, well, from J from 0 to length of gamma, 1 over the degree of the gamma J. So in square lattice, once again, what I mean that if we, for example, on the boundary of our domain, in this point we have 4 ways to go, each with probability 1/4, but if you go out, you are reflected back inside the domain. So you are kind of reflected back into this point. It will be the same thing as if you go with probability 1/3 to 3 sides. You just, if you go here, you reflect it back, so you have to do it again and again, eventually you leave, and the probabilities will be equal. So, so that's, the partition function is equal to 1, because eventually you get B, so the partition function of the random walk is the sum for all gamma 1 over 4 lengths of gamma is equal to 1. So it's an infinite converging sum, infinite because there are walks which infinitely long circle inside the domain, never reach B, but they take the probability 0 in the limit. And now what is loop erased random walk? So if you have random walk gamma, you get a loop erased random walk, which is, well, let's say denoted LE of gamma. So this is a procedure of loop erasure. So partition function for loop erased random walks, it's sum over all simple curves eta, and then you get sum over all gamma such that loop erasure of gamma is equal to eta 1 over 4 to the power length of gamma. So for example, this curve you can obtain as a loop erasure of many curves. For example, this curve itself or such curve is again loop erased on many others. So the difference between these two partition functions is that you take this one and then you group gammas with the same loop erasure and you get that function back. Or if you want to go back, you somehow simple curves, but each simple curve, it comes from many random walks. Now, what is going on? So suppose we want to decide where to go from point, well, from some point A. Maybe we have drawn already something. We want to go to U1, U2, U3. So if you draw random walk, you can exit through U1, but then maybe after loop erasure you hit it back and you erase. So what we do, we take all the random walks, for each, take last visit of A. Well, let's say it's AT of AT. Take all random walks which where loop erasure of gamma starts as A1 and so on, AT, and take the last visit of AT. If it's the last visit of A1 and so on, AT. If it's the last visit of AT, then we no longer come back to this guy. We no longer come back to this guy. So we never ever can come back to it. So that means that gamma no longer hits A1, AT. And weight of gamma is proportional to 1 over the, well, let's say gamma no longer hits AT, and define, well, let's say gamma prime is gamma from this time onward. Then weight of gamma is proportional to weight of gamma prime, which is 1 over 4 to the power length of gamma prime. And gamma prime is random walk from A, C to B in the domain omega where you excluded this curve. So you are not allowed to hit this curve, so it's just a random walk in the remaining domain. So on the remaining graph. If you look at this graph as a domain in the plane, the appropriate thing is to say that it has Neumann boundary conditions. You're not allowed to touch boundary, means Neumann. It means that if you hit the boundary, they just push you back inside the ring. So it's... So this is okay. And then what we just compare how do you compare partition functions of the random walks from here to here, from there to there, and from there to there? They're the same as partition functions in the opposite direction, which are exactly the Green's function. So then the partition function of gamma prime from uj to b is exactly the Green's function from uj and b. And this is the probability that AT plus 1 is equal to uj. So that's basically the proof. The proof is very easy, and well, the important sort of thing is to say that once we finished off with the condition that we don't return to this part, it's just excluded from the domain, so we work on the graph which is without this part. If you want to look at the graph as a domain in the plane, it means that this part became boundary with Neumann boundary conditions. You're not allowed to touch. Not allowed to touch is Neumann boundary. So Dirichlet boundary conditions is when you say that the temperature on this wall of the room is equal to something. Neumann boundary condition is that it's just completely dissipates through it, so you're not allowed to touch, so you are reflected back, with the same as reflection back. So this is either you do random walk on this graph, or if you want to speak about this graph as a subset of the plane, you say you work on this subset of the plane with Neumann boundary conditions. So that's the difference. The difference once again is that if you just walk, if I erase this point and I walk on this as the graph, before it was what? It was that probability 1/4 in each direction. Now it's probability 1/3 in each direction. And probability 1/3 in each direction, it more or less means that I do this picture, I do 1/4 left, 1/4 right, 1/4 right, 1/4 up, but then I'm pushed back. So with probability 1/4, I stayed here. Now I try again. So I add 1/4 of 1/4, 1/16 here, 1/16 here, 1/16 here, 1/16 I go up, I'm pushed back, 1/16 I stay here. And when you expand it, doing infinitely many times, then it eventually will get 3 geometric progressions. So with probability 0 you stay here, and here you have 1/3, 1/3, 1/3. So it's small calculations which shows that Dirichlet boundary condition, reflecting boundary conditions, sorry, Neumann boundary conditions, reflecting boundary conditions is the same as just you exclude this edge from the graph altogether. Okay, so this is the loop erased random walk. And let me just formulate one more model. So this is exactly, well, the first curve is exactly like the topic of the course. It's some conformal growth, Laplacian growth. It turns out that it corresponds to loop erased random walk. And then there is another model, which is called UST. So it's uniform spanning tree. So we take discrete domain omega, well, let's say omega epsilon, as a graph. Take, well, let's say tau capital to be the all the t inside omega epsilon, which are trees. So I take all subgraphs which are trees and which are spanning. What does it mean, spanning? It means that it reaches all the vertices. So for example, if I take this graph 2 by 2, then there are 3 possible spanning trees. 1, 2, 3, well, 4. If I take this graph, there are many more variants. So I can, for example, well, there are really many more. So there is this, there is this, there is this, and so on and so on and so on. If I take, for example, 8 by 8 board, it's already a non-trivial problem how to count how many spanning trees are there. So uniform spanning tree is a tree T in tau taken uniformly. So the probability of T is 1 over exactly the cardinality of this set tau. So these spanning trees, they were studied by Kirchhoff, famous, well, at least now, okay, so Kirchhoff, I always sort of, no, I always screw up writing his name. So he has a book in 1847 on electrical networks. And there he, so basically what he does, he takes, for example, a graph like that, takes a point A and a point B, we are very familiar, and says what happens if if every H is a resistor with resistance 1, and we put current from here to here, how the current will be distributed. So he wants to calculate how much current goes through given H. So for example, if I go from this A to this B, it's clear that more current will go that way than that way. But how to calculate? And he observes that the current will be described by harmonic function, and then he observes that harmonic functions are actually related to uniform spanning trees. So Kirchhoff proves several theorems there in the book about electrical networks. He proves that you can, in a network which is a graph, you can calculate, you can write down the current in terms of harmonic functions, which in terms you can calculating the number of spanning trees.
Yes.
And the very surprising theorem which Kirchhoff did not exactly know, though he came close. By the way, he calculated the number of spanning trees through the spectrum of Laplacian. So there is a nice formula which relates it to Laplacian and to harmonic function. So the theorem which is due to David Wilson. So theorem. So it's Wilson. So suppose that I take a uniform spanning tree. In a tree, any 2 points are connected, and moreover, there is a unique branch from A to B. So there is, in a tree, there is a unique branch from A to B. And the rest of the tree looks something like, that. So there is, from any 2 points in the tree, there is a unique way to get from one to another. So the theorem of Wilson is that the law of the branch from A to B is exactly equal to the law of loop erased random walk from A to B, which in turn is equal to Laplacian random walk from A to B. In particular, branch from A to B and branch from B to A are the same, obviously. So in particular, it means that loop erased random walk is symmetric, which is not at all obvious from these two definitions. So the corollary is that loop erased random walk from A to B is equal to loop erased random walk from B to A. And then, in fact, there is the thing which is this, there is a second corollary of this, which is called Wilson's algorithm. You actually can Google internet, it will show you the Wilson's algorithm in action. And it's actually an algorithm which tells you, it's kind of more general than spanning trees. It tells you how to deal with certain Markov chains, and so there is a more general thing which is called Prof. Wilson. So Wilson's algorithm tells you how to build a UST. So what you do, you start with 2 points, A and B. You run loop erased random walk. So you run loop erased random. So you start with, let's say, 3T contains 1 point, and you choose A. Run loop erased random walk from A to T. T now has 1 point. And then you take T1 to be T union with this loop erased random walk, with this new curve gamma. Then you choose A1, run loop erased random walk from A1 to T1. So you run loop erased random walk from new point A1 till you hit this one. Then you choose new point, run loop erased random walk, choose new point. So the Wilson algorithm tells that eventually you construct uniform spanning tree. So to choose a tree uniformly, you can run loop erased random walk, then you can run loop erased random walk to this loop erased random walk, and so on and so on. And eventually the structure you get will be exactly a tree. Well, that's by construction, but it also will be chosen uniformly from all trees. And it's much faster way to get a uniform spanning tree than the other ways. Which, well, for square lattice there is one better one, but in general it's probably the fastest way. Okay, so those are the three models. Let's take a short break and then we'll show that they are related to SLE if they are done on the plane. Okay, so we need to calculate something for loop erased random walk and to show that it converges to SLE. And it turns out that effectively Kirchhoff already calculated it ages ago. So at the time when this SLE appeared, Rick Kenyon, by very, very difficult methods, showed that loop erased random walk is sort of a fractal curve in the limit which has dimension 5/4, which indicated, so Schramm knew about this result, it indicated that it should be SLE2. And the proof doesn't use Rick Kenyon's theorem and gives a so it's, let's say, a theorem. Okay, so it's Loewner, Schramm, and Werner. And it says that loop erased random walk. So if loop erased random walk is a random broken line on a square lattice in some domain. So we take, let's say, take omega epsilon discrete, which in some appropriate sense converges to omega is epsilon goes to 0. So it's the lattice mesh. Then loop erased random walk on omega epsilon converges to SLE2 on omega. So of course what is meant that you have domain omega, you have points A and B. Here you have omega epsilon, which is the discretization of our domain. So we have point A epsilon, which is near A, B epsilon, which is near B. You do here loop erased random walk. You get a random curve. So the meaning of this is essentially, so the meaning is that loop erased random walk is measure mu epsilon, which belongs to the measures on, for example, space of curves from A to B. For example, it's a space of continuous functions up to parameterization. And what is meant is that mu epsilon converges to weakly in weak topology to measure mu, which gives us SLE. So SLE is measure mu. For example, weak star topology, so those are barrel measures on something. Okay, and for the uniform spanning tree, I need a little bit, maybe more to have it nicely. So uniform spanning tree is not a curve, it's a tree. But what you can do, you can walk on a tree using right-hand rule and you get a curve. So we do the following boundary conditions. We force the part of the boundary between A and B to be included into the tree. So we take UST, which is rooted, so it's called rooted on the arc AB. So it means that this arc has to be included into UST. So we condition that AB is inside our tree T. And then there is a curve. There is a curve which follows left-hand rule. So let's say call it piano UST curve. So there is this piano UST. And it's space filling. So this piano UST on omega epsilon A epsilon B epsilon converges, and it has to be a SLE which is space filling. So it converges to SLE 8 on omega from A to B. So there are different ways to prove it, because for both of these models you can find many observables which will do the job. In principle, one can probably try to prove it without observables. No one did it in writing, but we know now enough to just try to identify this curve in some other way. But no one has put it in writing yet. So for observables, there are many observables, but then there are also some questions, a priori questions. So it's, for example, we discussed that knowing probability that you are to the left of a point is in principle enough. But suppose that our curve is very crazy. Suppose it satisfies this probability, but in some sort of obscure way, like it goes really, really crazy in different ways, goes around points with probability 1/2 its space filling. So you get some really strange things. So we have to exclude it. We also have to show that the curve is described by Loewner evolution. What do I mean? For example, the first curve, what can happen? Suppose that you have a curve which is simple on a lattice, but which goes like that. And then in the scaling limit, that will correspond to this behavior. So up to this time, it's a simple curve, but here it's no longer simple, it touches self, but it goes inside the fjord, which for conformal observer is not visible. So SLE doesn't see this, Loewner evolution doesn't see this part. So if something like that happens with loop-erased random walk, what it will mean that we will describe our curve beside those detours which we won't see. So, so the theorem I prove then just means that the Loewner part of our curve is described, but there might be some other funny things. So you have to exclude these funny things. For loop-erased random walk, by the way, it's very easy. I won't do it, but it's very easy. It's essentially means, suppose that you indeed have this thing. So it means that from this point up to this point you have drawn this guy, and from this point you should be able to escape with random walk without hitting the boundary. But it's very, very, very unlikely that you escape from this point without hitting the boundary, because you have to, it's like sailing through a narrow fjord when you are a poor sailor without hitting the left or right shore. So that's is incredibly small value, and when it pinches, it sort of goes to zero, so it's impossible. So there are, what I'm saying, that one has to address these concerns. There are two ways to address these concerns. So what Loewner, Schramm, Werner do, they take discrete curve, describe it by Loewner evolution. Discrete curve is nice. Say that the Loewner evolution is driven by something which is not Brownian motion, but close to Brownian motion. So they do the same calculations we did yesterday, but with not exact martingales, but approximate. Then the driving force is approximately Brownian motion. And then they show that it converges to Brownian motion, but write a lot of estimates. Another option is that you assume that, or you prove that there are no such things, and then you already work in the continuum setting. So there are well, either this or this approach, so it basically depends what kind of approach. It's like constructing Brownian motion. It's, you can do some work and construct it as a process which is almost surely a Hölder curve, or you can for free construct it as a process which is some curve, possibly discontinuous, possibly jumps around, but constructed for free. And then you prove that it is Hölder. So either way around, it's sort of a philosophical question. So what I say that we don't do a priori, this sort of a priori or a posteriori, we don't do estimates. So what we need, so we assume, we take for granted three things. That first, there is a subsequential limit. So gamma epsilon j converges to gamma. Second, so our martingale, we'll calculate some martingale for gamma epsilon becomes martingale for gamma. And the third one is that gamma is almost surely a Loewner chain. So there are various ways to do it. For example, Scott Sheffield, he has a way which says that it's sort of if subsequential limits are simple curves, then you get automatically to other things. Me and Nancy Kempinen, we have a way which says that, so for example, it's enough or sufficient to know that basically probability so if we have some sort of a picture which goes like that, and we have a curve, well, we have point A here, point B here, and we have sort of a fjord in the domain, that probability that gamma enters annus is O small of R over R, as R over R tends to 0. So if you have things like that, that probability of entering small annus is small, then that basically is enough. So I don't want to show that this is enough to do all these things, because, for example, already Loewner chain, you need to check several conditions, that the point moves continuously, that you don't loop around, so that would have taken 2 hours or 3 hours of estimates. But in a sense, one property is enough, and this property for loop erased random walk is automatic, because Brownian motion is, which is from A to B, is very unlikely to enter deep fjords. And it's for SLE 8, one has to do something separate anyway, because it's a space filling curve, so it's already a bit wild. Okay, so I don't do this a priori estimates. Now the martingales for UST and loop erased random walk. So the easiest one is the for loop erased random walk, and it's sort of a cheating in a sense that so lemma. So we have sort of this picture. We take point Z. So what I'm saying is that G, the ratio of the Green's function from A to Z, A is the tip of the curve. Let's say A of Green's function from A to B is a martingale. So I'll write the proof and then I'll explain. So we draw the curve. So we need to, well, let's say you know this by M of Z. Well, it's strictly speaking M of the domain, omega, A, B, etc., A, B, Z. So the proof, it goes like that. So what does it mean that it's a martingale? So we need to take the expectation of M of Z when we draw our curve for one more step. So there are 3, or possibly 2, or 1 possible steps. So it's the sum of probability that we go to Uj times martingale of, now we had a domain omega, now we have domain omega minus Uj of Z. Now, this is the sum of Green's function from uj to b in the domain omega minus uj, which sum from Green's function omega from a to b, and the martingale is Green's function from omega minus uj from uj to z, because we continued our curve, and it's normalized by Green's function in omega minus uj from uj to b. So that's the martingale, and those are the probabilities. And this thing cancels out. So we get the sum of Green's function omega minus uj from uj to z divided by Green's function of omega from a to b. And this one sums to Green's function from a to z, as we already discussed, that a to z partition function of random walks from a to z is the sum of partition function of random walks from u1 to z, u2 to z, and u3 to z, because you just take the last exit from a and you sum these random walks. Well, basically, why now it looks a little bit like cheating, everything cancelled out, but essentially, what is a martingale? Something, if you have something which is defined at the last moment when we hit our point, probability of event, expectation of some variable, etc., and then you filter it, you take conditional expectation with respect to your curve, then you have a martingale. So that's just the usual theory. Now, what happens, we define something in our domain, so it's not the last moment, so a priori it can go as it wishes. But we normalize by the partition function of our model, so it's automatically a martingale. So it becomes a martingale because we normalize by g omega ab, which is the partition function of our model. So probability of our model configuration is given by this. So this is the partition function of the loop erased random walk from A to B. So anything which we normalize by it, we automatically can think of as a event, as a some probability event in this final sigma algebra. So when we normalize by it, we automatically get a martingale. So that's the sort of a trick that we normalize. We take some object and we move it. We take this object, GAZ, and then we move it into the space we want, the probability space with respect to this measure. So then it becomes a martingale. Okay. So it's kind of, if you're more into probability, it's what is GAZ? It's a partition function of random walks from A to Z, or loop erased random walks from A to Z. It's not our model. So what we do, we weight it with respect to the partition function of our model from A to B, kind of, if you know measure theory, Radon-Nikodym derivative, and it turns out that this becomes a martingale. Okay, so this is a martingale, and this is basically a Green's function. So it's a Green's function, function or Poisson kernel, if you wish, because it's Green's function on a boundary. So we can write exactly what is its limit. Actually, by the way, here I realize that you even don't need that. You need to show that this is smaller than 1 minus epsilon, because once smaller than 1 minus epsilon, then you can do telescoping things further on, and then you get to small. So in fact, it's easier even to check. Okay. So what happens is that so we take now subsequential limit, take any subsequential limit of loop erased random walk. So the measure mu epsilon converges weakly to measure mu. So if we show that mu is SLE2, that will imply not just convergence of this subsequence, but a convergence of any subsequence. So it implies convergence. So if we show that mu is SLE2, it will imply that a loop arrayed random walk converges to SLE2. Because if it does not, then there is a sequence which doesn't converge, which is converging subsequence. We apply it, and it converges to SLE2. So if you show that any converging subsequence converges to SLE2, it has to converge to SLE2. Now, what we do, what happens to this thing is that as epsilon j goes to 0, g of az over g of ab converges to the Poisson kernel at z. Because what happens? So A and B. So you have a ratio of two things, which is harmonic inside, 0 on the boundary, and blows up at this point. So it's equal to, well, wait a second. So what do I have? Yeah, it blows up to this point and normalized at that point. So it blows up here. So it's basically the only way is Poisson kernel. And then Poisson kernel, of course, the question is how you normalize it. You can multiply it by constant 10 or constant 11. So we normalize it by that it's equal 1 in the immediate neighborhood here of this point. So it's if you step 1, well, you normalized at point B. Z normalized at B. So it's because this function, well, let's say m of z. So m of z is harmonic, blows up at A, and normalized to 1 at B. Harmonic, 0 on the boundary of omega, blows up at A equal to 1 at B. Now, suppose that now what we do, we map our curve, map omega to half plane, describe gamma by Loewner evolution. So we have a picture that we draw a curve gamma t, then there is a map gt, which maps t to 0, at gt is z minus at plus twice t over z plus so on. And martingale, so what is the martingale, what is the Poisson kernel in the half plane? Who remembers the formula? What is the Poisson kernel? The function which is 0 on the boundary blows up at 1.0. Maybe the easiest thing is to, well, I mean, you can do real formula, but the easiest is to think in terms of complex numbers, because it's, if you take complexified, it's an analytic function which blows up at this point, and whose imaginary part, whose imaginary part is 0 on the boundary. So the function is, imaginary part of 1 over z. It's also, you can write it as y over x squared plus y squared. Am I correct? X plus iy times x minus iy. Yeah, I think that's it. Minus probably. Yeah, okay. So the martingale we're interested in, so the martingale is minus imaginary part of 1 over gt of z. So this will be a martingale. Now I want again to emphasize that this function is well, this is a real function which is 0 on the boundary just by the formula. Now it blows up at 0. It blows up at 0. At 0 it's y over y squared. And it's normalized, in my case, at infinity. Why? Because gt has always the same expansion at infinity. So no matter which t I plug in, it will have the same expansion at infinity. So it's the same normalization by GAB that is here. Normalization at infinity is given by normalization of g of t. So it's a martingale. Now what we can do, let's say, so it's a martingale. Then we have what? We have 1 over z is equal to expectation. Well, imaginary parts everywhere. Imaginary part of 1 over gt over z. It's expectation of imaginary part 1 over z minus at plus twice t over z plus so on. It's imaginary part of expectation. Now we have to do Taylor expansion of 1 over z. So it will be imaginary part of expectation of 1 over z minus plus at over z squared plus at squared minus twice t over z cubed plus so on. So this is just a check, maybe for exercises, check that this indeed expands to that. And then we can equate all the coefficients. So we conclude that expectation of at is 0. Expectation of at squared minus twice t is 0. Then we do same thing for t and s increments, and we get that at and at squared minus twice t martingales. And then we get by Levy's theorem that at is square root of 2bt, so it's SLE2. So that's essentially the proof. As I said, I skimmed a little bit over the a priori estimates, so you need to check that random walk is not crazy, some condition like that, and then check that because of that we can choose subsequential limit. It's almost surely described by Loewner chain, and we can play these martingale tricks. So that's it. But otherwise, I mean, ideologically, that's the proof that you get a SLE2. Now, a uniform spanning tree, let me, so we have 10 minutes, yeah, that should be ample. So for uniform spanning tree, it's essentially, well, the required martingale is already in Kirchhoff's work. So what we do, we introduce a third point C on the boundary here. And if I take point C on the boundary, there is a unique curve which connects it to the arcane B. So take, so UST. Take UST rooted on the arc, bless you, AB. So we have, yeah, this picture. Fix C on the arc BA. So it's a picture, something like that. Let eta be the branch which connects C to the arc AB. So it's something like that. Now for U on the dual lattice, so it's one of the centers of the cubes. So this is a point U. we write f of u, well, f is bad letter, let's say p of u, is equal to probability for this UST that, let's say, u is right of gamma. And then we take a different model, which I'll call 2UST. So this model is a forest of two trees. So 2UST is two trees. The first one rooted on AB, and the second one rooted at C. So it's basically a model where we cover everything by union of two trees. So there is a model which is called uniform spanning forest, where you cover everything by a number of trees. Here it's a forest, but it only has two trees. Tree number 2 at point C, and tree number 1 at point AB. And I denote another function q of v, where v belongs to our lattice, to the usual lattice. And let it be probability in the new model. Probability in the new model 2UST that v belongs to this upper tree. So v belongs to the tree number 2. So tree of the point C. So a small lemma, P of u plus I q of v is discrete holomorphic function. So it turns out that these two functions together, they bring discrete holomorphic functions, but I need to slightly normalize because we, well, maybe the best one was to just count them, how many trees like that are there. So it's maybe, you know, another definition is, well, what is the good one? So I need here to put a coefficient which is the number of configurations with two trees over number of configurations with one tree. Yeah, something like that. So the equivalent thing is that the following function, that the number of USTs that u is right of gamma plus I number of these forests where v belongs to the tree number 2. So this is a holomorphic function. Yeah, that's the same thing. So this, as I said, it was essentially known to Kirchhoff 170 years ago. And the proof is rather easy. It's sort of an easy woodcutting game that you sort of chop trees and reattach them back. So let me write what is the first function. Let's say let me write what is p of u1 minus p of u2. So this is probability that, well, okay, maybe I'll write number of UST such that u is right, u1 is right of gamma minus number of USTs that u2 is right of gamma. So that can you can rewrite, if both of them are right of gamma, then it contributes to both of these things and cancels out. If it's both left of gamma, again, it contributes to both of these things, so it cancels out. So what remains is that its number of USTs that U1 is right of gamma, U2 is left of gamma, minus number of USTs that U1 is left of gamma, U2 is right of gamma. So let me draw this as a picture. So this is my block. This is A, this is B. This is, let's say, my points U1 and U2. This is point C. When does it happen that U1 is right of gamma and U2 is left of gamma? It happens when you have a picture like that there is this curve which passes something like this. So it has to pass through this edge. There is no way else to separate. Now you can ask a question. What happens if it's the other way around, that U1 is left and U2 is right? How can this happen? It should separate them, but it should separate them in different direction. So there should be a twist. So it should go like that. By the way, on this picture it looks that this picture is more likely than that one, because in that one I need to twist. But if your domain is very large, size of 1,000,000, all pictures, they will include many, many twists, logarithm of 1,000,000 twists. So this one is not much more likely, it's just a little bit more likely, because generic picture, if you draw it on computer, you see there will be logarithmic numbers of twists back and forth, so it's not. Okay, now a woodcutter comes with an axe and he just kills this edge. So what happens if he kills this edge? You get, instead of a tree, you get a forest now with two trees. And the two trees, one contains C and one contains AB, exactly as we had. So it's, let's say, V1, this is V2, and this is again V1, V2, and then you have this sort of picture. And the first picture is number of these double forests where V1 belongs to tree 2 and V2 belongs to tree 1, minus number of these two tree forests where V2 belongs to tree 2 and V1 belongs to tree 1, which is again the number of double forests where V1 belongs to tree 2 minus number of double forests where V2 belongs to tree 2. So basically we have shown that the derivative of the first function in the direction of from U1 to U2 is the same as the derivative of the second function on a lattice from V1 to V2. So there is this sort of, as you remember, Cauchy-Riemann equation tells you that the derivative of a function in one direction is the same as its derivative in a direction rotated by 90 degrees times I. Or it tells that the real part derivative should be the derivative of imaginary part in the direction at 90 degrees. So that's exactly the discrete analytic thing. So it basically means is that so two functions, number of USTs where our point U is right of gamma, and the second function, number of WSTs that V belongs to tree 2, they're harmonic conjugates. And if you normalize them as probabilities, so what happens if you normalize them as probabilities? So when I am here A, B, this is C. So if I'm here, I'm always right of the point Z. So here, P is identically equal to 1 on this arc on the right. Here on this arc on the left, P is identically equal to 0 because I'm always left of it. So this is P equals 0. And the bottom arc, I know the discrete values for Q. For the bottom arc, I know that Q is equal to 0 because you belong to the bottom arc, you don't belong to the upper tree. Q equals 0, which actually means that normal derivative of P is equal to 0. So it turns out that we have a discrete solution of the following problem, that our function is 1 here, 0 here, its harmonic conjugate is 0 here, so it actually, so P plus this IQ normalized. So it will converge to the function phi, and the function phi will be given by a conformal map. So what's the good way to do it? So it's essentially the map to a strip of width 1. So map to such a strip, but I only need to rotate it properly. So P, well, yeah, I screwed it up. I should have put it the other way around. Yeah. So it's, so what did I say? So P U1 is right of gamma. No, I didn't screw it up. So U is right of gamma, it's the other way around. Yeah, so sorry. So U here is U is right of gamma. Well, U is right of gamma almost, no, a second. U is right of gamma. So it's probability, no, that's okay, yeah. And what I don't get P plus IQ, I think probably it's IP plus Q, because derivative of P is derivative of Q, so P plus IQ, so it should be the other way around, yeah, because this is 90 degrees. So it's P, if it's P0 and 1, wait a second, I didn't look at my notes, but I think it's, no, I think it's correct. It's P plus IQ. Yeah, everything is normal. Yeah, I don't know why I'm, yeah, so that's, yeah, of course, that's what I've, yeah, okay, P is equal to 0 with 1. So it's a map to a half strip like this one. So this is, so phi is a map to half strip. So here you have real part equal to 1, here you have real part equal to 0, and here you have imaginary part equal to 0. Yes, yeah. And somehow, yeah, so everything is correct. Okay, so what we don't have time to do is to do the calculation. So either I will do it beginning of the next lecture, or we'll do it during the exercise session. So the first question is, what is the formula for this map. What is the formula which gives you the map to half strip? So it's a, well, famous function you learn in school. Well, not when it's 0 to 1, but anyway, yeah. So it's a sort of a well-known function which gives the map from half plane to this, and then you get that phi of z, phi of gt of z is a Martingale, and then you deduce the value of kappa. Okay. So what we do next time? Next time we'll do percolation, which is in a sense much easier, because for percolations, all the a priori estimates, they were worked out by people long before. So there are some easy probabilistic arguments which are as easy as for random walk and much easier than for uniform spanning tree to do the estimates that almost surely you get a nice curve and etc., etc. And the argument is basically more or less the same. It's sort of a rearrangement of the things. So if you didn't grasp it, we can go over it next time. But again, it's a very easy piece of combinatorics. So Kirchhoff did it in his book on electrical networks in 1847. Okay. So he actually sort of calculated the current through this edge as the number of trees which go like that. This number minus that number.